All right. Do I start, Ibrahim? All right. Can you guys see my screen? All right. So اليوم هنعمل ريكاب شو درسنا last week و then we'll move on. I'll tell you شو هنعمل for the next week. So for this week. So last week حكينا عن what is a neural network and أخذنا example of predicting house prices. فأخذنا multiple inputs. We used an algorithm for this example وعملنا we predicted an output. ونeural network عرفنا it's an algorithm that you used that takes an input and we have an output. وبعدين كمان حكينا عن the differences between deep learning applications and we can use it on machine translation, we can use it on computer vision and autonomous driving. Okay, so في كتير applications where we can use neural networks. Every neural network, every application has a different way of doing things. وكمان تعلمنا why deep learning is taking off. We learned about the three things: computation, experimental, and algorithms. There are innovations عم بتصير but there is a computational limitation. As this is increasing, it will allow us to experiment more, which will allow us also eventually to innovate more. For this week, I'll be talking about the basics of neural network, and when you implement a neural network, there are some techniques that are going to be really important. And I want to talk about when you organize the computational of a neural network, you usually go for something what's called a forward propagation step, then followed by a backward propagation step. And this will allow you to understand the computation of a neural network. And it could organize the forward and the backward propagation. And so for today, I will convey all of these ideas using a logistic regression. Just to make your ideas easier to understand. But this could be applied to not only binary classification, it could be applied to anything. And even if you have seen logistic regression before, I think it will that you'll be seeing new interesting ideas for today. So yeah, let's get started. So logistic regression is an algorithm of binary classification, and here's an example where for a logistic regression problem is that we have an image that we'd like to recognize if it is a cat or not. So for the binary classification, we either have two possible outputs. It's either 1 or 0. It's different than what we did last time, where we were predicting a price of a house, where we had multiple or infinite possibilities of outputs. Here, since it's a classification and a binary classification, so we have only two outputs. And here, the outputs are either a cat or a non-cat, which is 0. And we know this as y. So let's look at how an image is representing in a computer. To start, an image in your computer stores three separate matrices as red, green, and blue. And you can see here that this is how the computer understands this image. So it does not understand it as a cat. And you can see all kinds of images are a combination of RGB, red, green, blue. So it takes a bunch of red matrices, green matrices, and blue matrices. And let's say that your image is 64 by 64. It's a very low resolution image, but this is just an example. So you'd have here a 64 matrices for the red, and 64 matrices by 64 for the green and for the blue. And so you'd have around 6 by 64 by 64 corresponding RGB. It describes the intensity of your image. So to turn these pixel intensity values into a feature vector, okay, what we're going to do is to unroll all of these pixels into an input vector X. So for us to actually put things into to features, we need to use these as features to try to predict this. And these are not really understandable, or it's very difficult for us to play with. So we have to unroll all of these pixels and into a vector where we're going to define this vector X corresponding an image. So we can have like X here is equals to a matrix, a vertical matrix, and it's say like 255. It would go one by one, so 255, then 231. This is not a 64 by 64, but imagine it is a 64 by 64. And go down until 202, and then it would go again to 255 again to go for the green matrix. 255, 134, and so on. Okay, and we would have around 64 by 64, 64 by 64 3 times. So these are 64 by 64 numbers, and we have it 3 times. So we would have around 100 122,088. So this image is a 64 by 64 image. The total dimension of this vector would be 64 by 64 by 3. That would give you the total number of these images. So what you got is what you multiplied these numbers. We call them n of x. So n of x is the number of rows of how much the data is. And to present the dimension of input feature x, sometimes we can also use the notation nx to represent the input features. So we have again more than 100,000 of input features, and we call them nx. And basically, we have to go over some notations before moving on to understand more other examples moving on. So a simple training example is represented by a pair called xy. So let's put xy here. Okay. And x, as we saw previously, belongs to n of x, and y, since it's a binary classification, it's either only 0 or 1. Okay, so again, what we explained so far is that we unrolled the images, the pixels, we put them into a vector, and then we have all of these numbers, we call them n of x, and we have y, which is the output. It is only two possible outputs. It's either a 0, which is a not cat and one if it's a cat. And we also have something called which is a training example. One second. And we have here in the training example, so x1, y1, and x2, y2, and so on until we have xm. And so basically, we have the training examples by the length of m. And we can also say that we have something called mtrain, which denotes the training example. And you have something called mtest, which is the number of test examples. Sorry. Okay, number of tests. And we have an example of an X is we would see that we have a big capital X. Okay, where we would have a column of all of those feature X's. X2, and so on until xm. And if you want to, this is basically the size of m. This is the how many parameters that we have, and n of x would be how many rows that we have. So m is how many columns that we have, and nx would be how many columns of x. And when you want to go on Python and you put x shape, you would see that you'd get an xm. So you get the size of the shape would be an xm. And this is essentially once you have a vector, and this is how we're gonna be using it later on when you want to implement a neural network. You're gonna be seeing it in this kind of shape, and where x here, the capital X belongs to an x. And basically, we have to do the same thing for y. But y, since we only have, we have to multiply it by x. It's going to be only has to be the same number of m, but it's going to be only one row. So it will be y1, y2 until ym. Essentially, because with all of these features, it's for x1, it has an output y1. So in another example, we have a bunch of features in the first column where it says, okay, this it predicts 0 in this example, and it would go for for every x, it would have a specific output that we have for it. And also the same thing here. If you want to predict, if you want to go to Python, you'd always see that the shape of y would be 1m, and y dot shape is how the Python notation of the Python notation of how you want to write it to get this shape in Python. And it turns out to make your implementation of neural network easier, you have to stack the y in columns. Okay, and again, this is basically how you use these notations to understand the use for logistic regression. And we will use this a lot to fetch out logistic to use these a lot in logistic regression. So you will see these kind of notations a lot. So if you don't understand something, just let me know in the future slides. هلا we're going to be talking about logistic regression. Okay, logistic regression is just a learning algorithm that you use when you want to output labels y in a supervised learning problem, where you either have zeros or one, and it's mainly for binary classifications. So when you have a problem and you want the outputs to be between 0 and 1, one of many algorithms is logistic regression. So we're not only limited to logistic regression, we have so many algorithms, but one of the binary classification problems is logistic regression. And logistic regression basically gives you an input feature, x corresponding to an image. So let's say we have a given x. Okay, and you want to predict y hat. And essentially what y hat is an estimator of y. And basically y hat is the probability of the chance of y is equals to 1. So y hat is equals to the probability of y is equals to 1. So it's just a prediction, a probability of y equals 1, given what we give x. So given the features of x. All right. So it is a pretty simple understanding of y hat. Y hat is just once you predict something given the features that you gave it from x, we want y hat to be as close to 1 as possible, because y is the truth label compared to the y hat. So in other words, if x is a picture, like we saw previously, you want y hat to tell you what is the chance that this is a cat picture. So if you get like a 0.7, it will tell you, okay, the 0.7%, 70% chance that this is a cat picture. So x, as we said earlier, is an nx dimension vector that the parameter of a logistic regression will be w. So we have to give some parameters w. Okay. W is just parameters that are in x, in an x dimension. Okay, and it takes a real number, which is b. Okay, so given an input x, the parameters w and b is how we have to generate the output y. So since we have the parameters, we have the x, we need to find the output y hat. And one of the things that we can say is that y hat is equals to w transpose x plus b. And this is very similar to, this is a linear function of an input, but this would unfortunately not be a very good algorithm for binary classification, as we saw that a linear function would go to a very big number, and it could be also a very negative number, and we need to limit those numbers between 0 and 1. So here, this should be 0 y hat is between 0 and 1. So we need to limit the function of y transpose x plus b. Also, this is a given function of logistic regression. Why is it transpose? Sometimes people get confused. Why is it transpose? It's we usually do transpose so we can multiply the vectors together. As we saw in the previous slide, we had x, which was an x by m matrices multiplied by a 1 by m matrices for y. And to multiply the matrices together, they have to yeah, I have to have m as the common inside, and so that's why we have to transpose it always. So this is not a very good function. This is not a very good algorithm, because we want y to be between 0 and 1. And to enforce this, we implement something called a sigmoid function. So a sigmoid function is all of this, okay, but with put it here, it should be here, something that looks like this. This is a sigmoid function. This is what a sigmoid function looks like. And to plot it, if we have on the horizontal axis, plot z, okay, and sigmoid would be looking something like this. To go between, look like something like this. And so this is the sigmoid of z. And here it would be usually 0.5. And here, which is 1. This should be going closer to 1. Okay, and here you can see it's going closer to 0. So it goes smoothly from 0 to 1. And in the middle of the vertical axis, it goes to 0.5. And this is what a sigmoid of z looks like. And we're going to denote z here is, this would be z. So z would be w transpose x plus b. And here is a formula of a sigmoid function, where sigmoid of z is a real number. So 1 over 1 plus e minus z. So this is the sigmoid function, and essentially, if the z is large, we can see that the sigmoid would be 0, okay, and it should be equals to 1. And if the z is small, we can see it's a very large negative number, to be a very large negative number, and to be 1 over 1 plus a very big number, and it be closer to 0. So you'd see it here be 0. So let me write it down. If z is large, so sigmoid of of z would be 1 plus 0 equals to 1, and also the same if z is small, or it's a very large negative number, since if it's extremely large negative number, it would be 1 over 1 plus, let's just say big. Okay, it would be near 0. So notice, and you can see here, if the z is a very small number, it would be close to 0, and if z is a bigger number, it would be closer to 1. And if you notice a couple of things, z is a very large number, then ez would be close to 0, and this is again how it looks like. So when implementing a logistic regression, your job is just to try to learn the parameters w and b, so that you can predict y. And y hat becomes a good estimator of a chance of y is equals to b. This is basically what we're trying to end with. So this whole thing is just finding the parameters of x, and we have to make the output as close as the truth label. And when implementing a logistic regression, all you need to do again is to learn the parameters w and b, and yeah. So now you have seen a logistic regression model, how it looks like. Next, to train the parameters of w and b, you need to define something called a cost function. And to train the parameters of w and b, a logistic regression model will need a cost function that is used for logistic regression. And again, for the sake of this example, we're using logistic regression, but you can use an algorithm for each of a different application that you're using. So like we saw earlier, the W transpose X plus B, since we know it's a logistic regression, we put the sigmoid. If it's not a logistic regression, if it's a linear, we would not need this sigmoid function. So let us go there. So here is to recap what we have defined in the previous slide. Y hat over here, hat is a sigmoid of W transpose X plus B, where sigmoid of Z is 1 over 1 plus E to the power of minus Z. And to learn about the parameters of your model, here is the training set, given your parameters M. Okay, we have M training examples, and we can and then we have all of these training examples as we see here, and it seems natural that you want to find parameters W and B, so that at least on the training set you'd find y hat y, the outputs, which outputs are y hat y, and it has to be as close as possible to y hat, to yi. Yi is again the truth label compared to the y hat. Y hat is the predictor, what we're trying to predict, and we need to make sure that the prediction is as close to the truth label. This is what we're doing when we're training the model. And to fill you a little bit more on the equation on top, here we said y hat, but this is actually y hat I, and xi and zi. So we're doing all of this on one training instance. And we can see here, no matter if it is X, Y, or Z, we're just using this as an index of the ith example of where we are, and we use these superscripts to index the different training examples. Okay, and your prediction on the training example I, which is y hat, is going to be obtained taking the sigmoid function and applying it with W transpose X. And we take this for every single training. So here we have to also define something called the loss error. And what a loss error means is we can use how well we measure how we can measure how good our algorithm is doing. So to know if this was doing good or not, we need to compare the difference between y, the truth label, and the y hat, and we do this through something called the loss function. And the loss function usually is L, which takes y hat and y, and it would be usually a half y hat minus y squared. And it turns out that you could do this, but in logistic regression in specific, people don't usually do this, because when you come to learn about the parameters, you'll find that the optimization problem, and which we'll talk soon now about gradient descent, it will become a non-convex. So you end up with an optimization problem without a local optimum. So you'd have it going like this. And you can see here that we have a lot of local optimums, and it is not convex. This is an example of a non-convex solution. So gradient descent may not find the local optimum, and we use gradient descent to find if you want the lowest number, and we want this to be the lowest number, as this is the difference between these two numbers. So the lower the number it is, that means the more accurate that our predictions are. And the intuition to take away is that the function L, which is called the loss function here, it's a function that you need to measure of how good our output y hat is. So ignore this function right now. We don't need to worry about it. But the main idea is we to know if our function is doing well or not, we use something called the loss function. Okay. The actual loss function for the logistic regression is a bit more complicated than this. It is L y hat y. So essentially all algorithms would want to take a loss function, but for different algorithms that you're going to be implementing, they have different loss functions that are the most suitable for this algorithm. So you cannot be using the same loss function for any algorithm that you're using to avoid this kind of problem. So once you want to optimize your algorithm, it will be very difficult to optimize, since it's not going to be able to find the lowest number. And so here for the logistic regression, we have y log y hat plus 1 minus y log y hat. And this is all negative. So you don't have to worry, and I know that algorithms usually are a bit scary at first, so you don't have to worry about memorizing or really deeply understanding what this does bit by bit. But what we have to take from it is, again, we have to know which loss function that we're using, depending on the algorithm. And since we're using a logistic regression, this is the algorithm that we need. And mainly, most of the algorithms that you're using have a loss function already defined if you can search for them on the internet. And again, and what we said earlier is that we need to have the loss function to be as low as possible, since this is the difference between uh, the predictor and the truth label here. And since y hat can be either only between 1 and 0, it cannot be very big. Uh, Here we can say that if y, because here we're trying to optimize it as much as possible, if y is equals to 1, then the loss function, this would be 1 minus 1, which is 0, so this would be cancelled out, and it would just be minus y log y hat. And here we want log y to be large, and so we want y hat to be large. And here this would be actually just minus log y, because this would be 1. So it would be minus, it would just be minus log y. And for y hat to be large, we'd have as much as a negative number as possible. But again, remember, y hat will only be between 0 and 1. So the lowest number we can have in y hat would be 0. Okay, and the maximum that we'd have is 1. And if another possibility is that if y is equals to 0, then we would have so this would be 0, and you'd have minus minus 1 log 1 minus y hat. And here we want log y log 1 minus y hat to be large. As the larger the number, it would be the smaller the number. So we want y hat to be a very small number. Okay. So finally, what we need to take from this is the loss function is defined with the respect of a single training example. So all of this was done for a single training example. So when you're training a neural network, and you have seen like a number of epochs, and you'd say usually you'd put it like 200 epochs or 300 epochs, and so this was just for one epoch, for one training example, and we would know if this one training example was good or not. But to get to know if the whole the whole training was doing good or not, then we call something called a cost function. So a cost function would be for the whole training set, not like the loss function. So the loss function again was focusing on one training example, while the cost function is training for the entire training set. and it would be called JWB. And basically, this would output 1 over M. M is the training size, how big our training set is. And I would take a summation, since it's getting all of those loss functions together. Summation of M, and I take the loss function of y hat I into y hat. And we'd apply and see it would go through every single iteration. And here where y hat is, of course, the prediction of our output of our logistic regression, and using this particular set of parameters W and B, we would get this function, all of it. And just to expand this because we're going for the logistic regression, the loss function of this would be this function right here. So it would implement this, it would sum it, and it's all divided by M. And this function is not a static function. This would change depending on which model what we're using. But for simplicity, logistic regression is a very simple algorithm to learn, and you'd get the concept of how things work under the hood. And then if you get more and more complex algorithms, you'd still get the basic idea of how it's working. So all loss functions, their objective is still the same. They are still to find the local optimum, to keep the difference between y hat and y as close as each other. And so it doesn't matter how complex these algorithms can be, the goal is still the same. And when we want to implement this, we would still go through the same process, just the calculations might be a bit different. So the cost function is the cost of parameters in a training of your logistic regression model, and we're going to find W and B, the parameters that minimize the overall function cost. So all we need to do the process is to find and to minimize the overall cost function. Okay, and one second. Let me see if I just missed something. Yeah. So if you have just seen the setup of logistic regression and the loss function for the training and the overall cost function for the parameters for your algorithm, it turns out that the logistic regression can be viewed as a very, very small neural network. And yeah, so this is a very simple neural network. And I get it might be a bit overwhelming to see all of this at the first time. But with practice, it gets easier and gets more simpler, and the idea more marinates more, and you'll get the hang of it. And once you implement more of these, you'll understand. And again, I'm not trying to focus on the implementation itself, trying to tell you what is happening when you implement it. So it doesn't matter which algorithm you're using, it doesn't matter what you're focusing on. Everything is going towards the same goal. We're trying to minimize the cost function. We're trying to make y hat as close as y, and to have a better model to be way more optimized. And so, do we still have time, Ibrahim? Well, I can go on. we'll keep it until next time لأنه فيها a little bit more يعني maths وهيك ف I don't want to confuse them خلاص. Okay, so next time we'll talk about gradient descent وبنحكي what's happening. This is the recap of how the function is doing. So we saw إنه هذا this is the cost function هون. Okay, this is for the logistic regression وبتعمل a gradient descent to minimize the loss function as much as possible. We'll talk more in details on next time, and yeah, we'll explain the gradient descent. And gradient descent is one of the most important things that you'll do in machine learning. So you're going to be implementing gradient descent كتير. I will talk about this next week. All right, thank you.